Welcome everyone. Today we have the great pleasure to have Professor Richard Craster from Imperial College with us. So Richard is currently the Dean of the Faculty of Natural Sciences of Imperial College London. So you have the Department of Mathematical Sciences, but also the Department of Physics in this faculty. And Richard, besides from that, is also the director of an international research laboratory between Imperial College London and CNRS, which is a French National Center for Research. And well, everybody knows, I guess, who Richard Craster is scientifically. So please, Richard, you're welcome to talk now.
Okay, thank you very much for that kind invitation and for the invitation to talk. So this is my very first webinar, so it's a kind of interesting introduction to the new future, so to speak. I'm going to talk about elastic metasurfaces. So this is about designing surfaces to have particular properties. For those of you in the world of metamaterials and metasurfaces, you'll be aware that there's a lot of work on optical metasurfaces and also on acoustic metasurfaces, which has been highly successful and has allowed people to develop devices which are a very, very small scale, but which can allow you to manipulate light or sound. So this is about attempting to manipulate elastic waves. And so what would make elastic waves different? Well, elastic waves have, for those of you not familiar with elastic waves, there are two, if it's simply isotropic and homogeneous, there are two types of waves. There are compressional waves, which do this, and then there are shear waves. And they travel at different speeds. So it's a bit like, if you're familiar with Maxwell's equations, it's a bit like having E and H traveling at different speeds, which would be rather perplexing. We're rather fortunate in electromagnetism that E and H travel at the same speed. But in elasticity, the P and S waves travel at different speeds. That might not be too much of a big deal, except whenever they hit an interface or a defect, they tend to couple into each other. In fact, they have to pretty much couple into each other. So you're faced with a system where you have waves which travel at different speeds, they interact in different ways, they scatter off an object and they create both of them. An elastic surface, so if I take a block of material or the surface of the Earth, there's a wave which travels along the surface and exponentially decays with depth. That's called a Rayleigh wave. So these elastic surface waves are what cause earthquakes and things like ground vibration. The travel of ground vibration is basically, or typically, a Rayleigh wave. So Rayleigh waves tend to travel for very long distances on the surface. And if they hit a defect, then they'll scatter into both P and S waves. So P is compressional, S is shear. And so they will scatter into the body waves of the bulk. So there's a complicated interaction between waves on the surface and waves in the bulk. Now, what we would like to do is we would like to be able to control waves on surfaces. We would like to be able to, if we have a wave traveling on the surface, we might want to direct it in the plane. We might want to change its direction. We might want to turn a Rayleigh wave into a compressional wave, into a shear wave, or maybe backwards even. And so why would we want to do that? Well, we might want to trap energy at particular places. We might want to divert energy off to energy concentrators, an acoustic black hole or an elastic black hole, so that the energy disappears. We might want to build devices so that vibrating machinery don't bother you if you live nearby, or if you're in the same building. You could have an isolated piece of your building which didn't suffer from vibration. Many of the motivations for elastic waves involve the non-destructive evaluation of structures. So these involve finding cracks in objects. You might have a crack inside a nuclear reactor. So you might have a fracture or a flaw, particularly in an old nuclear reactor. And you might be kind of concerned whether you have them or not. But you can't send someone in to have a look. The only way that you can do this is by sending a wave, or one of the main waves is to send a wave into that system, maybe down the pipes or whatever, and then look at the reflections you get from it, and then try to understand what is it you saw. So trying to understand how you redirect waves is very important. How do you protect against ground vibration? or maybe you want to protect buildings against seismic activity. Another thing that you might care about is, can we use the vibration of machinery to extract energy? So we all care quite a lot now about, quite rightly, about conserving energy, what's going to happen in the future. The one thing we could do is what's called energy scavenging, trying to get little bits of energy from different places, so that when we have sensors in awkward positions or awkward places, we don't have to spend our time going and replacing the batteries, and we don't have to dispose of the batteries which contain unpleasant heavy metals. So there's quite a lot of interest, practical interest, in why we would care about understanding and controlling vibration. A typical issue that we have is often that we want to control low frequency long waves. So the noise that bothers you in the evening is when your neighbor is playing loud music, you hear the bass noise coming through, and that's because you have low frequency long waves and your walls are relatively thin relative to the wavelength, and so the energy goes through the system quite easily. Can we build devices which are smaller than a wavelength? So if we think about the wavelengths of some seismic waves, they'll be hundreds of meters, tens of meters long. We don't want to build devices made from concrete which are tens of meters, hundreds of meters long. We would prefer to build smaller things. And how do we control waves with small things? Well, one way to do that is to use resonators, because resonators resonate at a frequency, but I can make the resonator small. Or maybe I can make clusters of resonators which interact with each other. So this talk is about how we create those sorts of objects and about ideas and devices which use these concepts. I'm going to be talking about something called rainbow trapping, or about how do we frequency select spatially. So I want different frequencies to arrive at different places and then pull the energy off. That's primarily what this talk is about. The sorts of interesting things that happen in the world of metamaterials and metasurfaces are John Pendries, our colleague in physics, came up with Pendries Lens, which goes back to work by Veselago. If I take a block of material which has a negative refractive index, and I, for instance, put a source in the middle, I can then get an image outside. So this is now bending light, so it's typically done for light, in directions that you don't normally expect. You don't expect this anomalous refraction type of effect. Well, what this picture is showing is what happens if you take this block of material and gradually make it thinner and thinner and thinner. Could you get an effective negative refractive index, but on a line? And if you could get it on a line, then maybe you could shrink this device, if we think of it as a device, down to literally almost zero thickness. So this is work with Greg, who's one of my PhD students. This is a simulation of electromagnetism, or for elastic plates, where you have a dipole, you send the signal along this line array, and when you grade the array after a certain point, you can tune it so that this acts like a self-phased array in some sense, and then you get this beam going backwards and you get this focusing effect. So you can trick the material so that it does the same work as this flat lens. Although in this case, we've got a source in the middle and we're focusing outside. We're not putting a source outside and getting a focus on the other side, although that is possible using this design. So these are the sorts of things we want to do, but we want to do them for elastic waves and elastic half spaces. So this is a simulation by Jacopo Maria de Ponte, who's a PhD student in Milan. So this is an elastic half space, and as with a source in the surface, if you take an elastic half space with a source on the surface, you get a Rayleigh wave, and the Rayleigh wave trundles along the surface. Here we've put an array, so an array of different heights of elastic beams or rods on the surface. And what we can do is, as we tune their heights, we can get this to apparently filter into compressional and shear waves going backwards and get a focal point. How does this work? Are we truly separating P and S here? How do we judge this angle? Can we design this so that we get these angles in any direction we want? And if we can we then apply these ideas Are they specific to elasticity? Are they completely general? And can we apply them to other places? So I think we'll hopefully see that as we go through the talk. As a kind of an interesting aside, the work of Philippe Roux is on, for instance, taking these ideas or ideas which are similar and actually applying them in a geophysical context. So there are some lovely experiments, and they're detailed on Philippe's group's webpage, where you take a forest of trees. So these trees are resonators. You don't think of them as resonators because we don't normally vibrate trees on purpose, but they have resonances of about 40 hertz. So this is, in some sense, a resonant array on the surface of the Earth. And there are some nice examples there of, does this work? Does it have the effects that we think it does? And it's important to think about the real problem, because soil is not necessarily linearly elastic. It can have non-linear, can be slightly plastic. So it's not always the case that physics reads the theoretical papers. Physics can sometimes be, the real objects can have losses and other mechanisms that we may not necessarily be thinking of. So now, what have we done in order to look at this system? So this is a picture of a simulation of an elastic half space. The first thing is, of course, on a computer, you can't do an infinite half space. So to prevent spurious reflections from the edge of your computational domain, we use something called perfectly matched layers. If you put a source on the surface and you excite the surface, you see a Rayleigh wave trundle along. There are a couple of bulk waves which are shed from this surface, the forcing that you put on the surface. It then interacts with this array. Let's make the array all the same height, all the same spacing. Now, if we had an infinite array, all the same height, all the same spacing, it turns out that we can analyze a single one of these in a very, very deep column. And what we do is we look at the phase shift across this object and then compare that to the frequency, or understand what frequencies correspond to what phase shift. And that's called the block problem. And the resulting pictures we get are called the dispersion curves. So this is the block wave number, which in this case goes between 0 and pi over 2. And And what we see here are, for the particular parameters we've chosen, that if we plot frequency versus wave number, we get what are called we would normally call them light lines, but we're dealing with sound here, so let's call them sound lines. We see the dispersion line for a compressional P wave. We see the dispersion line for a compressional shear wave, and we see the dispersion line for the Rayleigh wave. This tells us that Rayleigh waves propagate slower than shear waves, and compressional waves are much faster than everybody else. When we look at the array when they're all the same height, we have resonances, we get straight lines in this dispersion picture, and those correspond to the resonances of the rods. And the blue lines are of the system that we're actually studying. So the P, the S, the Rayleigh, and the straight lines are all part of the kind of background picture of our physical understanding, and the blue is what we actually see. For the actual system, what we see is a very tiny band gap. So in between this red dot and that bit, in that very, very narrow frequency, there will be a stop band. So if I was to send a signal at that frequency, it would not propagate through the array. But this is so tiny and so infinitesimal that it's very hard to actually get, even numerically, let alone in a physical system. So this means that if we were to build things all the same height, it would probably not be a very useful band gap, and we couldn't use it for many things. What we see, though, is that as we change frequencies, we can see that our waves change in character from Rayleigh waves to shear waves. So there's something useful going on here, but perhaps making them all the same height isn't particularly useful. We can see, if we investigate this a little bit more and we look at band pictures and frequency pictures and wavelengths as we approach the band gap from above, or if we approach it from above or below, we can see that as we enter the stop band, we do indeed get no propagation, and as we move up in frequency, we get to a point just below the band gap where this Rayleigh wave has slowed down and slowed down and slowed down, which is also a sort of interesting and useful point that we will return to. As we go down in frequency, we find that our wave changes its character from being a Rayleigh wave locked primarily to the surface into appearing more like a shear wave as it begins to propagate much deeper below the array. And those are sort of interesting features, but once again, having an array all the same height is kind of not enormously useful because of this very, very narrow band gap. So what have we done? So this is taken from some work with Andrea Colombi, Daniel Colquitt, Philippe Roux, Sebastian, who's also here. We investigated what happens if you grade this. So why would we care about grading an array? Well, we would hope that locally to a particular rod, that locally it would be behaving in a similar fashion to a rod in an array where they were all the same height. And so we could use the insight from our model problem to help us design for this graded problem. And we can obviously grade in two ways. We can send waves from short to high, or we can send them from high to low. If we send them from short to high, what happens is that the wave slows down, and eventually stops. Well, why would we care about that? Well, what we would find, is that different frequencies would stop at different places. So we would have a frequency selecting surface. So different frequencies would stop at different places. And when a particular frequency stopped at a particular resonator, it would stay there for quite a long time, and it would feed energy into the resonator, and you'd hope to get large amplitudes. If we did it the other way around, so what do we expect to see here? Here we expect to see a wave change from a Rayleigh wave into a shear wave. And that's what we see. We see a Rayleigh wave turn into a shear wave, and we see a wave or a beam propagate down at a specific angle. So if I think about these in terms of devices, what could we build? Well, in what I've termed here as the classic meta-wedge, we would have like a surface Fourier transform. So we'd have like a physical Fourier transform. We would select different frequencies at different places. And we might be able to extract energy from that system by taking advantage of the wave slowing down and arriving at different places and making a large amplitude. The other one, we could imagine we would be sending waves in and then changing their type, changing them from a surface wave to a bulk wave, and sending it in a direction of our choosing. So we would have built a surface device that would send waves and then direct them somewhere else, and actually leave a region quiet on the surface if that's what we wanted. So that would be a kind of nice thing to do, and we might ask ourselves, does this theory actually work in practice? The other thing about making it a graded array is that one of the issues that I described earlier when we had them all the same height is we get an incredibly narrow stop band. It's kind of useless. It's a narrow band, well, not entirely useless, but it's not particularly interesting in some ways. But because it's so limited to only acting at a very narrow band of frequencies, it's not very versatile. And ideally, you want broadband performance. You want something to operate across a whole range of frequencies so that your device then becomes really functional. And what happens when you use the graded system is, of course, that because different frequencies are doing things at different places along the array, that the device itself does begin to become broadband and have the performance that you would hope for, but across many frequencies. There are some interesting side issues, and I thought I'd pull this one up for interest. This is also work with Philippe Roux and his colleagues. This is what happens if you take a system of resonators and you start introducing a bit of disorder. So there's a kind of natural side question is, what happens if you don't make a perfect device? Is it terrible? And this was motivated by the kind of precursors to the experimental work that Philippe and his colleagues did in forests, where in this case they were looking at what happens if you put geophones in a forest and you start measuring ambient noise or the noise of cars going by. This is incidentally the noise of this is incidentally the peak caused by road traffic. And you know, do you actually see in experiments the band gaps, etc., some of the predictions that you make from this theoretical system? And the answer is yes, you do, which is rather reassuring. The next question is, does it really work? You know, so it's fine as a theoretician to come up with some grand plan or some grand scheme, but you've never any guarantee that the physics will read your experiments. You know, the physics might not. And so we were very lucky in that Matt Clark and his colleagues who work in ultrasonics in Nottingham came and built this. So they didn't build a forest, they built an array of tiny pins in an aluminium block. So another key thing is that these ideas are not necessarily dependent on scale. So the geophysical problem, you're dealing with tens of hertz, hopefully down to units of hertz, 5 hertz, but you know, of the order of 10, 20, 30, 40 hertz. But if you scale it, and hundreds of meters or 100 meters in size, if you scale it down in size, you're going to scale it up in frequency, but you can use the same ideas for ultrasonics. So instead of hertz, we've now got kilohertz on this side, and our sizes are of the order of a couple of millimeters. And we get the same dispersion curve type idea when we do the theory. Now, what about experiments? So what happens? In the world of ultrasonics, you can excite an almost perfect Rayleigh wave. This is how the non-destructive evaluation or crack detection on surfaces is done. Industrially, this subject is very widely used. If people want to look at the structural integrity of an aeroplane or an oil refinery, people will be sending Rayleigh waves or flexural plate waves up and down and through the structure and looking at the reflection. So exciting a perfect Rayleigh wave is something that these people do on a daily basis. So a Rayleigh wave is excited, so it lives on the surface. It then hits this array. This is the one where you have frequency selection. We typically send in we don't send in a single perfect frequency. We send in a range of frequencies, a tone burst. And then, as we see here, the waves are primarily localized into the array, and then they're reversed back exactly like we think they will. If we look at, so these are simulations, so this is now going the other way around. So this is us going high to low. We have the surface wave coming in. This is a picture on the top. These are from experiments, and the bit in the middle is from a numerical simulation. So we can see the wave coming in. It's localized into the array. The array is beginning to shed the shear wave into the bulk. It sheds the shear wave into the bulk. You get the signal on the bottom, and then it excites a Rayleigh wave on the bottom of the sample, which then trundles along. So this is experiment and theory working very nicely together, as we would hope. What happens? So the features, the kind of big ideas to take away from here are that different frequencies arrive at different places. When they do, the amplitude of the resonators gets very large. So if we wanted to think about energy extraction, we've got the beginnings of a device here for energy extraction. If we do the decreasing of height, we have waves coming in and then being shed off at particular angles. So here we've got a device which is turning surface waves into bulk waves, and us having the beginnings of control. Although this particular way that this is particularly done at the moment is that we're only getting shear waves, and they're only going forwards. They're not getting to be propagating backwards. So there is a couple of deficiencies and things that we might want to think about there. So let's think about energy extraction first. So this is joint work with Jacopo and Andrea and colleagues from Milan. So let's actually think about, can we really take energy off this system? So let's take an elastic plate. So let's not take the halfspace, let's do something simpler, an elastic plate. Put an array of rods on that surface, and then see, can we localize at particular places? Can we extract energy from it? It works in a very similar fashion. What happens is that at a particular frequency, in this case 215 kilohertz, we have a resonance, and we can figure out what spatial position we will have the maximum amplitude. We then put on this rod, we then put some piezoelectric patches. So this has the same effective height. We've just played around with it by effectively moving that mass further down and putting as we'll see, a propeller shape on the top. This then flexes up and down, thereby allowing the piezoelectric patches to be stretched and compressed so that we can extract energy from them. So at the resonant frequency, they will flop up and down. And when they do, we can extract energy from them. There's a nice Massspring dashpot type of model, which Jacopo put together, which allows us to have some analytic handle on this particular problem. And then we can ask ourselves, then we can actually numerically pull out the power difference. Does it make a difference? You know, we could just have one of these objects on a plate and, you know, measure the energy that we can extract from it. Or we could embed that inside the array. What's the difference in the power take-up, or the power that we can take off? Well, the power we can take off in the case of the graded array is much substantially higher than that of the single harvester. So very recently, we've been able to actually do this experimentally. So this has moved in recent months into experimental work, and this has now been verified experimentally, which is very, very pleasing. So I'm sorry, I realize I'm whizzing along without, for some reason you can't see the audience, so I can't tell whether there are any questions. Does anyone want to ask any questions?
Richard, may I ask you one question? How do you convert mechanical energy into some other type of energy? You convert mechanical into electrical, into...
Yes, yeah.
Okay.
This is done using piezoelectric patches. So there is an entire subject which is about piezoelectricity. It's a field in its own right. And so Jacopo and his colleagues in Milan, that's a group that specializes in piezoelectric patches and the extraction of energy from mechanical to electrical energy. So I can't give a talk on piezoelectric patches, partly because I feel that other people would give a better talk, and partly because it would take up an entire talk.
And regarding the experiments, they were made with what kind of material for the metasurface?
They're made exactly with the same design. I think it's an aluminium plate with aluminium rods.
Okay. And you put the piezoelectric patch just in the defect?
So the defect, which is here, that is a long aluminium rod. And on the top of it, so this is the rod, on the top, I'll put these piezoelectric patches. If you think about the patches, what happens is as they flex like this, the motion, which is stretching and compressing, is turned into electrical energy.
Via the strain.
Yeah, so in this case, it's like a little propeller. They flop up and down like this. And as they flop up and down, they get stretched and compressed, and that then turns into electrical power.
Okay, thank you.
As I say, I think people who work on piezoelectric patches could probably do a better job of explaining than me, but that's broadly speaking how it works. So thus far, we've talked about trapping waves, redirecting waves. Kind of looks quite nice. It works. There's experiments. But we only got shear waves and they only went forwards. Is it possible to get compressional waves? And the waves only ever went forwards, they never went backwards. So what level of control do we have over the angle? What level of control do we have over, can I take Rayleigh to P? Can I take Rayleigh to S? What can I actually do? And the answer is yes, you can do both. You have to steal some ideas or borrow some ideas from solid state physics. So this is this is described in a recent paper, which the details are below. And we're going to use an idea from solid state physics, which is called the Umklapp process. And it's from a different piece of physics, but one where they use Brillouin zones. Now, if we go back to an ungraded array, so we have an elastic half space, it's the half space now, not a plate, and they're all the same height. And we draw our dispersion curve. And what we do is instead of stopping at the first Brillouin zone, we continue to the second Brillouin zone. And what we do is we now look at so this portion here was what we were looking at before in the dispersion curves, not the full one. What happens if we are at a frequency up here, but we allow ourselves to think in the second Brillouin zone? What we see is a kind of continuation. This is a surface wave, apparently, on the surface here. And if I operated at this frequency here, well, I'd be outside that Brillouin zone. So the concept of what an Umklapp process is we're operating outside the first Brillouin zone, but we're only thinking about what's happening inside the first Brillouin zone. So this is the Brillouin zone that I'm thinking of, but I'm actually operating this purple circle would be the iso frequency contour of this if I was to think of it in terms of iso frequency contours. What I therefore have to do is I have to flip it back into the first Brillouin zone. And if I think of the wave number that I'm actually operating at in terms of the first Brillouin zone, I would get these angles of wave propagation. And what would happen is that the position I would have been at in the full Brillouin picture has been translated due to the lattice period back into the first Brillouin zone. And now, when I think of the wave number I'm actually operating at inside the first Brillouin zone, I'm operating at this wave number. And if I draw a vertical line at that wave number, I have an intersection. This is the iso frequency contour of the compressional wave. And the green is the flipped back iso frequency contour of the shear wave. And the red is of the Rayleigh wave. And the purple is from the system with the arrays on the top. So what happens under this interpretation is that my Rayleigh wave comes along, couples into the array, and is shed back in two directions. It's shed back as a compressional wave in this direction and a shear wave in this direction. Now, this is happening all along the array. So I'm seeing basically, I get a stronger signal at the beginning, but no matter where I am along the array, I'm getting both P and S shed backwards. So there's no distinct beam here. I'm just getting a kind of general shedding back of energy. But this is what in electromagnetism would be called a self-phased leaky wave antenna. So we're now making wave antennas, but on the surface of an elastic half space. That's ungraded. What happens if we start grading it? So now we start playing the game of changing those heights. So we're going to flip back. We're going to operate in the second Brillouin zone. We're going to operate at higher frequencies than normal. And we're going to flip back into the first Brillouin zone. Now, when we do that, we will find that different frequencies will be flipped back to different places. Now, if I can use that alongside the occurrence of a stop band, we will be able to flip back at particular places of our choosing for particular frequencies. So at this particular height, I might be cut off, but cut on. And then I would be flipped back and coupled in this case, to the P wave. So if we judge it correctly, we can tune surfaces so that different frequencies will be shared into different sorts of waves, and they will go in the directions of our choosing. Let's see some simulations. So this is an elastic half space. We send in our Rayleigh wave. It hits a graded array, so they're different heights. The rods oscillate, and they oscillate, or their resonances can be characterized as longitudinal or flexural. In this case, so it's longitudinal, but then it becomes flexural when we play this game we draw our dispersion curves, we get flipped back. It couples into the shear wave. It can't couple into the compressional wave because this contour does not intersect that vertical line. So we will only get shear waves back, and they will be directed back. And that's exactly what the simulation shows. When we do a forward propagating one, but we change the frequency, and we look at this surface and we see that in this particular case, the resonance that we care about is the longitudinal one. We get the flip back. In this case, our vertical line hits the compressional mode, and we have our surface wave come in, and it's converted only into compressional and along a direction of our choosing. So we're beginning to make a tunable, multifunctional elastic surface. It's fun. It's nice that it works, and it's also nice that we can take this idea of what's called Umklapp flip-over processes from a different piece of physics. So that shows us that we can separate our Rayleigh wave into shear only and compression only. What happens if you do experiments? So these are experiments, and this is going to generate a compressional wave. So our wave is tunneling into our surface. It hits the arrangement of resonators, is turned back on itself, and you get a compressional wave going backwards. And you can tell it's a compressional wave even by eye, simply by looking at the wavelength. So these are experiments. And this is the experimental setup by Matt Clark and his colleagues in Nottingham. So we got this to work, which was really quite pleasing. But you can tune it. You can get quite remarkable control. You can send in a Rayleigh wave and send a P wave off literally at right angles. So you have control over what you want to do. If you change the grading, then it's not quite as good. What happens then is that your array, all the points along the array, shed forwards or shed backwards, depending on how you orient your system. So it's not simply the case that you just grade it, send waves in, it's automatically going to do this. You do need the understanding of the flip over process and the position of the band gaps. So it's not, I don't want to deceive you into thinking that this is something you can just build and just run the system and it'll just work straight away. So this is a generic thing. Oh, I realize I've talked for 40 minutes. Maybe I'll speed up, but I think these are ideas which hopefully might be fun and interesting. What about water waves? So this sounds completely different. It's a completely different wave system. There's nonlinearity in water waves, there's surface tension, there's viscosity. You've no guarantee that water waves are going to behave like elastic waves or electromagnetic waves. But why don't we take a chirped array? Let's take some motivation from a group in Laum in France, Jean-Philippe Groby, Vicente, people who've worked on chirped arrays and acoustics. Can we do chirped ocean waves or waves in a long flume? So there's a long flume, 20 or so meters long, and let's just put, not even resonators, let's just put cylinders in there and change the spacing. And so this grouping in Australia, Luke, Malta, Jana, Hugh, and there's summer student Aidan, built this. And so, just to give you an idea that these are general ideas. So this picture is showing us these are the cylinder positions now going up. They're graded, so they're different spacings. This is different frequencies. These are showing us the positions of the band gaps. This is showing us the amplitude gain that you get. Different frequencies land at different places, just as in the previous thing. Here are some numerical simulations of a completely linear problem. The fact that the other one's slightly non-linear hasn't really made that much difference, thankfully. And when you measure the amplitude enhancement you get an amplitude enhancement of basically an order of magnitude. So this is a mechanism whereby you can take water waves, which carry a substantial amount of energy, if we think of the Earth, of us as a planetary system, and we can now think about how we could concentrate that energy in particular places and then try and take it off. Another thing which might also be of interest is acoustic metasurfaces. So I'm very lucky to be involved in a grant in the UK called which is run by the Physics of Life. It's with Mark Holderreid and his colleagues at Bristol University, and my colleague Yao Ting Wang, who's a postdoc here at Imperial. And it's an amusing grant because it's about life sciences. It's about how moths, the little animal, the little thing that flies around at night and then eats all your clothes if you're not careful, how does that evade bats, its main predator? It turns out that they are invisible to sound, or they reflect sound very poorly. And so this is a project about how do moth wings work? How do they not reflect when butterflies reflect very, very well? So if we look at the science of diffusers, this is a classical diffuser, QR diffuser, Schroeder diffuser made of different heights, based on quarter wavelength resonances. There's some really nice work by the group in Laos on Helmholtz resonating surfaces, and indeed by a whole variety of groups on space coiling and other systems. But they all have some physical limitation because you need the volume of the resonator, or you need a slit with some resonators off the side. Is it possible to make an acoustic metasurface using ideas related to elasticity, but make them as thin as you like? So these are some simulations of a metasurface diffuser which has a thickness of lambda over 100. So it's incredibly thin. And we're doing that, and this is a picture comparing it to a classical quadratic residue diffuser, and it's based on making an elastic surface, a membrane surface, with resonances that create a phase shift, and then using that phase shift to mimic what's going on in that diffuser. The main novelty is that this is now a membrane, not a bunch of Helmholtz resonators or similar. We can make a design which involves very thin elastic resonators and elastic plates, and then tune this design to get the desired phase shift. And indeed, you can use this to make multifunctional surfaces that operate. So at different frequencies, you get different effects. You can make this as thin as you like. So it's another way of thinking. It's a way of beginning to marry what we do in elastic metasurfaces to what's happening in acoustic metasurfaces. Finally, our group also works a little bit on topology, or in fact quite a lot on topology through Mehul. And this is related, although these are pictures of elastic plates, on redirecting energy on surfaces, but by using different lattices and different topologies. And Mehul gave a talk much earlier on in this webinar series entirely on that subject. So I think if anyone wants to know anything about that, then I think that will be a good, I'm basically putting in an advert or a pointer to a talk much earlier on in the webinar series. And so finally, I hope I've acknowledged all my colleagues and friends who've been kind enough to work with me over the years to have done that work. But I should also acknowledge the various funding bodies that have funded the work, a variety of national, international bodies, the French ANR, CNRS, some industrial companies. Multiwave was co-founded by Triffin, who was one of my postdocs. The UK Acoustics Network, I'll give a plug to the UK Acoustics Network. We now have 1,000 members, and hopefully will remain very active in the UK in terms of organising events. And my work has been, we've recently got a European grant, and I'd like to acknowledge it here as well. And hopefully I haven't talked for too long, and we've got enough time for some questions. So I'll hand it back to whoever's chairing in the hopes that I have at least one question. Or deathly silence.
Hello.
Hi.
I was just wondering, with regards to harvesting energy, what would substantial amounts of energy be able to be? Oh, sorry, I'm quite nervous. Would a substantial amount of energy harvested from quite geologically active areas, such as like near volcanoes and stuff?
I'm not sure about that because we haven't done those simulations for that precise problem. I mean, our interest is partly in scaling this down in size, so that if we think of vibration in awkward places where there are soon going to be lots of sensors placed in lots of places because sensors are becoming cheap and Wi-Fi is becoming ubiquitous. So I could imagine under a bridge or in some structure, we start to put hundreds, thousands of sensors all over the place. How's that Wi-Fi signal going to be powered? You know, it's going to have to report accelerometer data or something. And so we think nothing at the moment of sticking a few lithium batteries in. But once we have a few million of these sensors all over the place, who's going to replace those batteries when they're at the bottom of a bridge, somewhere awkward to get to? What are we going to do with all that chemical waste? If we could scale these devices down and even just harvest a very, very small amount of energy off them, we could perhaps keep those batteries going for longer so they didn't need replacing. Maybe we wouldn't need them at all. So that's actually the motivation of the energy harvesting. It's not to put them around volcanoes or in earthquake areas and energy harvest off earthquakes. It's a bit more, I don't want to say mundane, but it's a bit more practical.
So it's almost like you know, you get those small solar panels that you get on like road signs and stuff. They're just scale things. Then
yeah. So of course you would say, well, why not? You've just hit on it. Let's not bother with this. Let's do solar power instead. But if you're in somewhere where it's dark or it's night and day,
I understand you.
Yeah, there are a lot of reasons why you might want to harvest vibrational energy, and maybe I would even call this maybe energy scavenging. You know, because you're trying to get little bits of energy, and you might want to do this in places where it's dark, it's difficult to get to. Maybe there's lots of vibrational energy. Maybe you have some noisy machinery and you want to turn that noisy machinery into something useful. So the energy harvesting is, at least at the moment, we're thinking more of a different scale than you're describing.
Okay, cool. Thank you.
That's okay. You're welcome. Anything else? Or more deathly silence?
Richard, I have a question, if I may, please. Martin McCall here.
Oh, hi, Martin.
Hi.
Hi.
So in electromagnetism, at an interface where there is a change in sign of the dielectric constant, so at a metal dielectric interface, for example, that supports localized surface waves called surface plasmons.
Yeah.
Is there an analogous surface wave in elastic waves where there is a change in sign, say, of the bulk modulus?
I'm not sure. I normally think of the Rayleigh wave as the surface plasmon, to be honest. I mean, the Rayleigh wave operates as a surface plasmon. The dispersion curve.
Okay, so it's analogous to a surface plasmon.
Yeah, it's very, very analogous to one, yeah.
Okay.
We don't have the plasma frequency, but the effect of putting the resonators there introduces effectively the plasma, something very similar to the plasma frequency.
Right.
So when you draw the dispersion curves of a surface plasmon, my memory is you get some picture that does this, and this being the plasma frequency. This would be the equivalent of our surface Rayleigh wave, but with a resonator. That lower curve that I tend to show is analogous to a surface plasmon.
Okay, thank you.
Richard, can I ask a question?
Hi, Sasha. I recognise the voice.
And it's about metasurfaces. So if you think of a surface where you have rods of the height, which is not changing smoothly, but if you have abrupt change. So, for example, you have two arrays. One array is of height 1, and another one is of height 2.
Yep.
And then mathematically, you can think of transmission reflection problem for Fourier wave and associated with propagation along the surface. And of course, the effect is going to be completely different, but I'm just curious if this makes sense to look at the transmission reflection of a surface wave at a sharp interface when you replace one type of strictly periodic structure by another type of periodic structure. And of course, there will be some transmission reflection along the surface, but some waves may be reflected into the bulk.
Yeah. Sorry, Sasha. I was about to reply, and then I realized I cut you off by mistake.
No. Go ahead. That's pretty much what the question was.
Yeah. So what happens? One thing I didn't really emphasize was the quality, the lack of scatter. What you're seeing, for instance, in these pictures, you're seeing like an instant radio wave and almost all the energy going into a reflected shear wave. And the reason is that you're sort of tricking this so that the impedance mismatch is nothing. It's gradually turning into one thing and then suddenly changing. Whereas when you do material 1 into material 2, you often introduce what I'm going to call an impedance mismatch. I'm going to use a word from electromagnetism. But that sudden change will, I think, induce a large amount of scatter and a lot of energy conversion from, not from this into purely in this direction, but from this into basically a large amount of scattered noise, which is both P and S. It's certainly a good mathematical problem to look at, and certainly, I can well imagine using the techniques that you and I know of, material 1, half a line of material 1, half a line of material 2, put the junction in the middle, make a beautiful mathematical problem. And it would be a nice mathematical problem. It would be a very good mathematical, and it would be an interesting practical problem. But I just wonder, my feeling, I've not done that problem, was that you would get quite a lot of scatter when you go from material 1 to material 2, because the suddenness of that change will cause a lot of scatter from that junction.
Mm-hmm. Okay.
That's what I think will happen.
Thank you, Richard. Thank you.
That's right.
Can I ask a question?
Sure.
Hello, Professor Richard. Many thanks for your nice talk. And I want to ask you a question. So you mentioned that you can use MetaWave to harvest the energy by using the piezo. So what's about the power? What's your opinion about the potential applications? So it is possible to charge a cell phone? Many thanks.
Yeah. So you're stepping on to really making something. So Jacopo, who may be here, I'm not sure, and his colleagues in Milan, they recently built this for us. So they built our design, but our design is currently, I think it's like 2 meters long with big rods. So our current work is thinking about how to scale that down and then make it useful for what you're describing. And so I can't answer that because I don't know. I hope that this would work, but I can't promise this.
Okay, thank you.
Is there any other question?
Sounds like not. I guess I should thank everyone for coming.
Thank you, Richard, for the nice talk.
Good. I enjoyed it. It's the first webinar I've given, so yeah, it's an interesting experience. It feels rather strange. I'd normally like to go for a cup of coffee with everybody.
So thanks again. And as we said in the beginning, the webinar was recorded, and everyone who wants to ask a question, you can watch the seminar again on the website, and you can write the questions to Richard.
Yeah. Okay. Well, thank you very much, everybody. I guess goodbye.
Thank you. Thank you.
Thank you.
Thank you, Richard.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Thank you very much. Bye-bye.
Bye.